Welcome students. In this video, we will be doing the implementation of how to create a binary search tree. I think in the previous video, we just completed with what are all the properties of binary search tree. We were not very deep into binary search tree, but one property, main property that we want to learn about binary search tree is any node that you pick from a binary search tree will be having all the elements which are lesser than that picked element will be on the left side, all the elements which is greater than will be on the right side. So when you pick any element, left side you will have lesser element and the right side you have a greater element. And also we also have seen a procedure of how to create a binary search tree. So we take a element and we start the process from root every time, and if the picked element is lesser than the root, we move to left side, or else we will move to right side. And in doing the same process again and again, you some point of time you will find null where you need to stop. Suppose if 12 of left is equal to null and this is a place where we reached, we have to create a new node here, insert the new element, and that new node have to be placed on the left of 12 instead of null. Okay, fine. So now we will start with the implementation of the same, but the very important thing is actually the structure node is very important, because that structure node will be helpful in creating this node. So the first thing that we will do here is that we will, before creating a node structure, we will take stdlib.h inside which we have malloc. So for doing dynamic memory allocation, whenever we want to create a node dynamically, then we definitely want malloc, right? Fine. Now coming here to main function. Now first thing before main function, we want to first of all complete the structure. So we're going to take struct node, and this node is going to have, first of all, it is going to have integer data, and also it is going to have struct node star left and comma star right. This is the structure of the binary search, structure of the node of binary search tree we wanted. Now what are all the functions? First of all, we want to create a node, we want a function. To create a node, we want a function. And to create the tree, to make insertion process, okay, to make insertion. So now what we are going to do is we are going to write a function called as insert, which will carry out the process of inserting a particular node inside the binary search tree. And that insert function we will repeatedly call for set of elements so that the complete tree is going to be created. So two important functions that I require is, one is creating a new node and the other function is for inserting a new node. So creating a new node and inserting a new node, two different functions. Let me come to creating a node. I will create a node and I will send the address of the newly created node back. So I'm taking the return type of the function as struct node star. And this function is going to be insert. It's not going to be insert, it's going to be create node. Okay. So otherwise we can take this as new node because we're going to create a new node, right? So new node. What are all the data that is required to create a new node? No data required, but one thing, if I want to insert any element inside the node, I want which data I need to insert in the new node that I'm creating. So let me take a data which I wanted to insert there. So let me take that as X. So X is the new data that I wanted to place inside the new node that we are going to create. Now let us create a new node. So struct node star temp is equal to how to create a node here. To create a node, we will do malloc of size of what's the data type of a node is struct node. So it is going to be struct node. Data type is actually struct node, but what is the point? Because see, malloc will be returning you a null pointer. Malloc will be returning a null pointer. Null pointer, if storing it in temp, is useless. So we have to convert that null pointer into struct node star pointer in order to use it. So on the front side, I will do typecasting by giving struct node star. Now this is a procedure of creating a node. So we created a node, and by default, whenever we create a node, we mentioned very clearly in the concept, whenever we create a new node, the left and right is going to be having null at the time of creating a new node. So first thing is temp of left temp. So temp of left will be equal to null. So the new node created of left will be equal to null. And also temp of right, the right of the newly created node also will be equal to null by default initially. And one more important thing is in temp of data, we will insert the new data x2, which we need to place here. So this is argument x. And after doing this set of process, it is a complete creation of new node. And after doing this process, we will return the address of the newly created node. So we will create the address of newly created node. Now wherever we want, we can call this function, and this function will return the address of the newly created node, that you can receive it with the help of a struct node pointer. The address of the newly created node, you can receive it with the help of node pointer. Very simple. Okay. Now let us come to the function called as insert function, where insert function also will be returning the address of the root node every time. I will tell you why it is going to return the address of the root node every time. So the return type is node star, because it is going to return the address of a node. So return type, we are taking it as node pointer, and function is going to be insert. It's going to be insert, and let us take it as insert node. Okay, insert node. And what are all the data that is required to insert a new node? You just come back here to the structure and you see, if I want to insert a new element inside, first of all, the new element we will take and we will start comparing it from the root node. So the address of the root node is very, very important. The address of the root node is very, very important. So insert node, first of all, will be taking the address of the root node from where the process we are going to start. So let us take the address of the root node, and also what data I need to insert, that data also we will be sending here. So integer x. Okay. See, first of all, we will be doing an iterative implementation. And later we will do the later I will do the recursive. That not later, immediately after doing this iterative one, I will also create one more function for doing the same insert node operation, but in a recursive nature, how to do it. Okay, fine. Now coming to this insert node function, first of all, you will be here in the main function. Let us create a pointer for root node. So struct node star root. But by default, before starting to create a binary search tree, root will be having initially null, because still no node is inserted. So the binary entire tree is empty. So how to say that the entire tree is empty? If root is equal to null, tree is empty. So we are having root equal to null. Now let me tell you, for inserting a node at the root position, it is a different process. Apart from root, it is a different process, right? If it is a root, no need of checking anything. Create a new node, make the left null, right null, and make that a root node. That's it. Create a new node, make it as a root, left and right is equal to null. That's it. No comparison for the very first element. So inside this root function, inside this insert node function, the first thing that I will check is, okay, first thing what I will be checking is, I have to check if root is equal to null. Suppose if root is equal to null, no need of doing any checking. What we can do, actually, we can just simply return. What we can do is, if root, suppose if it is equal to null, if it is the first node that we are inserting, then first of all, let us call the function new node, and the new node function, we will also pass the data which we want to place in the node, and this new node function will be creating a new node, and it will be returning the address. So whatever address we receive from the new node function, shall we return it again here? Yes, that is what we are going to do. We will be creating a new node, and that new node address we are returning here. So when we return an address from this particular function, where it will be returned? It will be returned to the place where we actually called it. So where we called it, actually here, root is equal to, what I'm going to call is, root is equal to, I'm going to call the function insert node of, I will be calling, for example, I will call 89. The same, like same element, root node 89. So for the first time when I'm calling, also we need to be passing the address of the root also, right? So root comma 89. So for the very first time when you call this function insert node by passing address of root and also x 89, what is initially now the root is, because now the binary search tree is empty, so root is equal to null. So this root we are passing as null, so coming here this condition will be true because root is null. When root is null, we create a new node by calling this function, and it will be returning the address of the newly created node, which we receive here, and again that address, new node address, we are again returning one more time, we are returning again from this function. So new node, see, new node address is, see, new node is created here, address is sent to insert node. From insert node, with the help of one more return statement, it is again sent to main function, to the same line where you have called the function. So instead of this function call, this new node address you will be receiving. So that new node address will be now assigned to root. Yes, perfectly working. Now what your root is having? Now your root is having the new node created. It is having the address of the newly created node. Fine. Okay. Now we have to proceed with the next insertion. Suppose if I go with the next insert node, if I suppose go with the next insert node, what I should be doing? I will else suppose if root is not equal to null, which means already there exist few elements in the binary search tree. If root is not equal to null, there exists some element in the binary search tree. So now we are trying to insert a new element. What you will do, you will start your process from root. You will now check whether the data that you have received is lesser than the root of data, or it is greater than the root of data. Accordingly, you will move to left side or you will move to either right side. Now let me do one thing. I will be checking if the new element that we want to insert x, is it greater than, okay, is it greater than root of data? If it is greater than root of data, what we will do? If it is greater than root of data, we will be moving to the right side. Okay, I will just write. So if this condition is true, I want to move to right side because the new data that I wanted to insert is greater. I want to move to the right side of root. How to move to the right side of root? I can just simply do root is equal to root of right. Root is equal to root of right. So automatically it will take you to the, because whatever is the address of the right node is available in root of right. Take that address and store it again back to root. So now root will be pointing to the right side node. So see here, for example, if 100 is the element that we are trying to insert, we will compare it with the root of data 89. It is actually, x is actually greater than 89. So I have to move to right side. So where is the right side node address will be available? It will be available in 89 of right. So root of right, only address of the right side node is available. So we will be doing right equal to right of right. I mean right is equal to right of root is equal to root of right to move to right side node. So that is what we have done here. Suppose if that condition is not true, then x is lesser than root of data. You can ask me, suppose if it is equal. Binary search tree, you should not allow any duplicate elements. We are not going to take any duplicate elements as of now. So no equal to cases. If you are providing it, it is a wrong input and it is not going to work for that. Okay. So if suppose x is less than in root of data, you have to move to left side. So what I will do, I will just perform root is equal to root of right. So this, it's not root equal to root of right, it's root equal to root of left, because the new data that you are inserting is less than the root of data, so you need to move to left side. So if whatever element that we are trying to insert, if it is greater than root of data, move to right side. If it is suppose less than the root of data, then you have to just simply move to left side. And this if else process you need to repeat, not for only one time, until you find a root. Okay, until your suppose if you are moving to root of right, if root of right is null, you have to stop there. If your root of left is null, then you have to stop there. Okay, and remember one thing, I'll just tell you one thing. Remember one thing. Suppose if your root of, okay, suppose if your root of left is, okay, suppose if your root of left is null, you stop your root here itself, because when you have the address of this node only, you will be insert a new node to the left of this root node. So when the root pointer is coming to this node and you find the left node or left to be null, you don't go to null, you just simply see here, you simply you be here, let the root pointer be here, so that you can create a new node and you can place it in root of left. So a pointer is very much required when you are like looking at when you're about to move to null. You don't move to null, you stop in the node where you are going to move to null, and now you can proceed with your new insertion. You can proceed with your insertion. So if x of data, if x is greater than root of data, right side, else you have to move to left side. But also you need to ensure that, okay, I'll just take this if else and I will make a new condition here. If first thing is root of data, if x is greater than root of data, what it means? If x is greater than root of data, then the the element that we are about to insert is greater than the root of data, so we need to move to right side. But before moving to right side, let me also make sure whether, before moving to the right side, let me ensure that root of right, okay, root of right, is it not equal to null? If root of right is not equal to null, you can move to that particular position. Okay, fine. Now suppose if this condition is true, what you can do, you can do root is equal to root of right. Okay, fine. Okay, now suppose if, see, this is one thing. Okay, suppose what I'm telling is that, suppose if x is greater than root of data and at the same time root of right is null, then what you will do? So now I will just give you a solution for that. I will just write something, else if is if x is greater than root of data. Just simply check x is greater than root of data. Now what it means, if this condition is not true, only you will reach here to else if. So if this condition is not true, either what I can say is, if because of root of right equal to null, if the condition is not true, then only this condition will made true. You will reach this condition. Okay, suppose if root of right is not equal to null, then this condition will be true. Suppose if it is equal to null, okay, this condition will be true. So if root of right is equal to null, what we need to do, that's the right position of inserting the new element. Root of right is the right position of inserting element. So first of all, let me call new node for creating a new node and inserting the new element x, and let me link it to root of right. So I'm creating a new node and placing it in root of right where I actually found the null. Is it okay? Yes. And a similar thing, what I will do, a similar thing I will also check for the other, two more condition also I will be placing. The one more condition is, I will go with else if, one more else if I will go with, and that else if is going to be, if x is less than root of data, if x is less than root of data, and at the same time if root of left, because if x is less than root of data, then you will try to move to left side. So if now root of left, if it is not equal to null, then you will move to it. Okay, if this condition is true, then no issues. What you can do is, you can move root is equal to root of left, you can move to left side node. But suppose if your root of left is null, that is what else condition will be checking. Or else you can just simply write else if condition, else if suppose x is less than root of data, x is less than root of data. What it means, see, first time I'm checking x greater than root of data and root of right not equal to null. If this condition is not true, if this condition is true, none of this else if will be checked. It will not go for checking itself. Suppose if this condition become false, only I will come to the next else if. Suppose if this condition can become false because of the first condition, or else it can become false because of the second condition, or else it can become false because of both the condition. Suppose let me consider that it becomes false because of the second condition. Root of right has become null, that's why the condition is false. But root of x is greater than root of data is true, but root of right not equal to null is a false condition. So I will come here to else where I'm again checking whether x greater than root of data. So it will come to this condition only if this is true, and if this is true and this is false. When this is true, this is false, then it will be coming here and checks that the first condition is true. I'm ensuring whether the first condition is true. If first condition is true and the second condition is false, then definitely root of right is null. So this is the right place of inserting the new node. The same process I'm going to do here also. What I will be doing, if x less than root of data and root of left not equal to null, then I will simply move. If not, I found the right place of inserting the new element. So what I will be doing, I will be placing root of left is equal to, I will create a new node, and by inserting element x, and that new node address I will store it in root of left. So I have connected the new node to the left of the root. So these are the four things that I am checking. These are the four conditions that I am checking. Okay, these are the four conditions that I'm checking. I will repeat the same process again and again. We will be, I will be repeating the same process again and again. Okay, this four process again and again I will be checking until what? Until what we are going to do this process. I will write here while of 1, which means this loop is going to run for infinite number of times, but I will stop this with the help of two break statement. When I will be breaking, if a new element is inserted to the right of root, then if it is inserted, I can go for break and completely stop. If some element is inserted to the left of something, then I can simply break this out, right? Yes. So I can just simply break if an element is inserted. There is no other things that we are going to do. Am I right? Yeah, fine. Now coming out of your while, okay, now coming out of your while, this is a function which is having some return type. So you definitely have to return anything at any cost. So if this condition is true, you are returning the new data, because if root is equal to null, then you are returning the address of the new node, because here you want the address, you want to create a root node. For creating a root node only we are doing this process. In other cases, what we will do is simply we will return null. That's it. We will return null. But this return statement we will not receive. Only at the first time of calling, whatever insert node is returning, we will receive it with the help of root. After that, if you are using this insert node, we will not receive it with the help of root, because second time when you do root equal to insert node, definitely this return null will be executed, and this return null will reach here and root will become null. So if first time of insertion you just take the address, store it in root, all the other time of calling the insert node function you don't assign it to any other pointer, because definitely null will be stored here. Now I will be calling this insert node function, and let me pass the address of the root node, and I will pass the next element. What's the next element here? We'll just check with what's the next element, which 12. The next element is going to be 12. So root comma 12. And the next element we will take it as, it is going to be insert node of root comma 56. And the next one is going to be insert node of 34. And similarly, it's root comma 34. It's root comma 34. And similarly, the same function, what we will be doing, we will be taking it for 80. We will be taking it for 80, and then now after that it is for 100. Then it is for 120. Then it is finally for 93. So all the elements we have inserted now in the binary search tree. Yeah, fine. But how to check whether all the elements are perfectly inserted or not? That's a very important question, right? But if I need to check whether all the elements have been inserted properly, then I need to learn a traversing techniques. We have few traversal method, and that traversal method for tree we need to learn, and with the help of that traversal method only we can cross verify whether all the elements have been properly inserted or not. And after doing this traversal method, we will learn traversal method, and then we will implement a traversal method, and we will check whether the tree has been completely created properly or not. After making it sure, then we will move to the recursive procedure implementation of inserting a node in a binary search tree. So what we have done is we have inserted how to create with the help of insert node. So with the help of insertion technique of binary search tree, we are creating a binary search tree. Okay, so now we are creating a binary search tree. Now we need to verify it. So we need to check, to verify that we need to learn traversal method. So that is what we are going to do in the next video. So we will learn traversal method. We'll come to the same snippet again. We will implement a traversal technique and then we will proceed further. Right? Fine. Thank you, students.